angular velocity of my airplane or my satellite, and I'm in principal axes, I go from PQR to notation omega x, omega y, omega z. And I have a direction cosine matrix that relates the principal to the body axes. The angular velocities are going to be the same. The vector is the same, but the coordinate system is different. And I can find the direction cosine matrix into body from principal axes using the ide command in MATLAB. And that's going to give you, the ide command is going to give you three vectors, the eigenvectors. You should be able to draw them on a piece of graph paper and then make it a right-hand system. So by making a right-hand system, you just have to change the signs. You should get a duct tape or something. So if you multiply this out, you get these Euler equations. So if I had a disk, say I had a large disk that was spinning, a huge disk, like the stand of a flag or something.
If the x and the y vectors, omega x or omega y, were in the plane of the disk, then the z-axis would go through the center of the disk. That would be the largest moments of inertia, and Ix and Iy would be approximately equal. That would lead to coupling in the L and the M equations, and that would cause a nutation.
In this equation, and I had a disk. The question is, would it be stable? If I had a spinning disk here and I had some disturbance of torque, would this set of equations be stable if these were positive?
If Ix and Iy were about the same.
The equation be stable. The answer is yes, it would be stable. It would be stable. And that's where you get what they call the pole-hode and the, what do they say? It's the pole-hode and the intersection of the ellipsoids. There's a momentum ellipsoid and an energy ellipsoid that intersect that show you where the tip of the omega vector, how it oscillates as the disk rotates. Now, what does all that mean? How can I translate that to English? What does all these equations mean? Well, if you could imagine it as a disk, as a spinning disk, instead of the globe, so I'm going to kind of hide the globe if I can. If I have a spinning disk, and here's the omega vector, okay? The tip of the omega vector is omega x, is an omega x, y, and z coordinate. So that's the tip of this is the omega vector. If you put a disturbance in on this disk, what's going to happen is it's going to nutate like this. The disk will just rotate like that in a stable fashion. It will want to return. If you take your ring or something and spin it, that's what it's going to want to do. If, however, it was a pencil, suppose I had a pencil spinning instead of a disk. Now I'm spinning it like this. I'm spinning it. These equations then would still be stable. It would still spin. So when you see someone throw a pass, unless it's Peyton Manning, it's got a nice spiral to it, right? That's because it's like a spiral. So here's the thing. That's stable unless there's a disturbance. If that Peyton Manning pass hits a gust of air, then the pencil will nutate into a toppling motion, like so. Okay. Now all that comes from these equations. Last year I went through the stability. It's in Siddy's book, How to Do That. Since you're all airplane people, I don't need to go into some detail, so we'll go into as much detail as I have time for, but I want you to know the end results. The end result is, if I have a disk, it's always stable whether I have a disturbance on it or not because of these equations. If I have a pencil or a football and I spin it, it's only stable if it doesn't hit a disturbance. If it hits a disturbance, it will topple. Got it? Right? Got it. So, true story. We were fighting to get our satellite up with the Russians. The Russians had sent Sputnik up. They beat us. And we were racing. The engineers were racing to send it up. So they sent up a football-like satellite. What was it called? Man, Alzheimer's hit me. Can't remember the name. Anyway, Pioneer maybe. Maybe it was Pioneer. I don't remember. So they sent up this Pioneer satellite. It's fine. It's spinning. It's up. Yep, they're communicating with it. It's working. Well, we're not really communicating with it yet. Let's deploy the antenna. So they deploy the antenna. Give it a disturbance. And before our satellite had gone one revolution around the Earth, it was toppling. It was tumbling through space. Because our engineers forgot Euler's equations and the indications of them. Another true story. If you want to, yeah, Mike?
I actually had a question about terms.
Yeah.
On the first row of the very bottom matrix, should the last two be omega y, omega z?
Omega, yeah, I just copied those down. Need these two?
Yeah, it should be omega y, omega z.
Yeah, absolutely. Let's copy them all. Omega y. Thank you. Omega y, omega z. Thanks. So, if you were to take a satellite and send it from one orbit to another, say it's a communication satellite, or say it's Sandra Bullock and she's stuck in space and she needs to get to another orbit level to get to the next space station, right? Before you shoot her up there, what are you going to do? You're going to spin that satellite, right? Because if you shoot her up there with just by applying thrust and you don't get the thrust right in the center of mass, you're going to tumble the spaceship. So you will spin the spaceship, then you will apply thrust, and that spinning motion will give you a nutation, right? Which will be relatively stable, again, as long as you're spinning about the major axis of the satellite. If you're spinning about a minor axis to the satellite, then you had better have some kind of control system working, because as you punch that satellite up to go to a hard rate, even though it's spinning, that spinning motion, angular momentum will tend to go into a tumbling motion. Got it? Okay, so here's your assignment. We've got this matrix that we derived yesterday. And what I'm saying is that you know your moment of inertia matrix in body coordinates. I give you one over here. And you know your sensor outputs in body coordinates, PQR. But my equation is written in principal axes. My equation is written in principal axes. These matrices that you see here are what you have to do to get this equation written in principal axes. You have to do this. So I want you to fill that in with both matrices, the symbols, and the numbers, because I gave you the matrix, right? So you can use PQR, but if this matrix shows up, or this matrix here, you should put this matrix in here, and then these matrix here, write it out once with the symbols so I can see you did it right, and then write it out with the numbers in there. The numbers for the matrices. Okay. What's that worth? 10 points. 5 points for writing it out with the equation, and 5 points for having the numbers right. So this will test your knowledge. Okay. All right. Let me tell you how to do it now. Okay. So how do you do this? I think it is. All right. I'm in principal axes. So this thing has to be in principal axes. So what has to happen? This first term over here must be this term over here. So this has got to be P dot, right? That's the P dot, I dot. So that's the first thing you got to fix. So fix that in your notes right now. So what happens over here to go from body axis to be in principal axis? Transformations, yeah? I'm just going to talk you through it. I'm not going to put them down. All right? So just listen to me and then get it right and work with your group. So what do I have to do to get this in the principal axis? C into P from B. What does MATLAB give you? Yeah, and after you fix it, you're going to get C into B from P. Right? MATLAB gives you C into B from principal axis. Or if you fix it, if you fix the left-hand system to a right-hand system, the transpose will work for the eigenvectors. That'll get this vector to dots in principal axis. This is in body axes. So what must these two matrices do? These two matrices must take this and put it in principal axis. So to have a coordinate transformation for a matrix, I need to pre-multiply and post-multiply. For a vector, I only need to pre-multiply. For a matrix, I have to pre-multiply and post-multiply to get it into. Now think about it. If this is acting on the vector in principal axis, so it's got to go, or in principal axis, this whole thing has got to be in principal axes, right? It's got to be in principal axes. So this has to take it into body. The body has to change the matrix and then has to go back into principal axes. This multiplication of these three matrices is called a similarity transformation. It's called a similarity transformation. It's how you change the coordinates of a matrix. Okay? So we know how to change the coordinates of a vector, and now we're going to learn how to change the coordinates of a matrix. I'm going to let you play with that. Okay? See what you get. But when I'm done, what are the product of these three going to be? The product of these three are going to be this diagonalized. And where am I going to get that diagonalized from? Eigenvalues of the eigencommand. The eigencommand is going to give me the eigenvectors, and it's going to give me the eigenvalues for the principal axes. So MATLAB is going to answer most of the questions you can check. That takes care of this term. How about this last term? Well, again, this last term, this has to take it into principal axes right here. And then right here, I have the cap omega vector in body axes. And once again, it's a matrix, so it has to pre and post multiply to take this into principal axes. Okay? And when I get this in principal axes, what am I going to have? Omega z, omega y, and omega x. Okay? I have omega z, omega y, and omega x. But you're going to have to work it out because it's not given to you. Right? So you work through this. It's going to challenge your meat circle, but it'll challenge you in a way that'll nail this notation down and show you how to go from one axis to the rest, and then you'll be dangerous out there because you'll fully understand how this stuff works and how these matrices work and how the notation works. And once you understand how it works, I don't mind if you simplify and start dropping the commas as long as you understand what you're doing. Yeah, Peter.
In the RC, you asked for the DCM that would diagonalize it.
Right.
But since you have to pre and post multiply,
Yeah, when you pre and post multiply by the DCM, the
so
triple product,
it is the same DCM.
the triple product, if you do it right, and do that in MATLAB, after you get the DCM from MATLAB, pre and post multiply this matrix and see if you get a diagonal matrix. And see if the diagonal elements of that matrix equal the eigenvalues that you got from the MATLAB command. Then you'll be real dangerous, right? Because you'll think you know what the hell you're doing.
So you
Right?
for that, you just want that one
I've been there before. It doesn't last long. Don't worry about it. It's a good feeling while it lasts, you know? Yeah.
So when you ask for the DCM, you just want that, since it's essentially the same thing, you just want that.
Yeah. Fill in this with symbols and then fill it in with numbers.
Okay.
Right? And if you have any questions, come see me Thursday night. We can go through this again. But I want to make sure you nail this down. Okay. So